Hi, good afternoon, everyone. So, first of all, I'm very thankful to Simpa and ICTP to give me a chance to speak about my research and to give lecture on finite element method and some other topic of numerical analysis. Actually, I'm very thankful to give me this research opportunity to work with Professor Andrea, Professor Professor Andrea Amiani and at Sisa, Italy. So in this visit, I try to sharpen my skill and try to collaborate with the group of Professor Andrea and the professor of Sisa. So actually, my main research area is numerical analysis. So I will speak on the topic for the numerical simulation and analysis of some parabolic PDEs using finite element method and differential quadrature method. So first is finite element method and second is differential quadrature method. Actually, I will start with finite element methods, then go to the differential quadrature method. So total, I have speak on eight lectures. So this course is just for the beginner who want to start the finite element method for partial differential equation. So in the first part, I will start some basics basics requirement for finite element method, because you know that the finite element is totally based on the functional analysis. So functional analysis. So in this series of lectures, I will cover some basic fundamental which required from functional analysis for the finite element method, and then at the second step. At second step, we will start the finite element method for first order ODE, or you can say finite element method for one-dimensional problem. Then go in this way for the two-dimensional. So and in the end, we will go for the finite element method for parabolic PDEs. So these two things are occur in elliptic PD, and this this goes to parabolic PD. So in parabolic PD, the time-dependent problem came in picture, and so how to do their analysis and their simulation by using the finite element method. So first thing in finite element methods come from the motivation. Motivation for the finite element method. Why why people start to do finite element method for solving differential equation or partial differential equations. So actually in before that there was finite difference methods. Before finite element methods, so people solve PD using the finite difference method. So we write its finite difference method, FDMs, and these method start in 1750. These are very old methods, and till now people are working on finite difference method, but in the hybrid type of finite difference method. So first, actually, it start in this one, but this become famous. Finite difference method become famous in the early of 90s, or you can say in 1928. In 1928, Lewis, Fry, and Richardson used finite difference method for weather forecasting, and try to solve, because in weather forecasting partial differential equation occur. So this guy start finite difference method for solving PDEs, because in weather forecasting the PD occurred. So after that, in 1940, finite difference method become popular for the you can say the for some practical problems. So until now, people are working on finite difference method. That's fine. So, but the finite element method are the younger than the finite difference method, and these methods in starting used by some people 1960, some engineers, you can say 1950 to 1960. Firstly, these method was used by some engineer, and these are some well-known engineers: Turner, and Argyles. For what? For structural engineering. A structural engineering for the aeroplane, you can say aircraft, for aircraft wheels. Means for structural engineering, they use the finite element method for modeling purpose, and after that these methods become very popular, and these days you can say there is a vast, you can say it's a big sea of finite element method. And in these methods you can solve OD, PD in terms of elliptic, parabolic, and hyperbolics. So these are very popular method these days. But initially it was a simple classical finite element method. After that, these days, then mixed finite element method, and then DG method, and many more methods. And these days, the HHO methods are very popular. Which are the advancement of the finite element methods. So now I come to the point of motivation, why the people start the finite element method, or you can say why the community of partial differential equation people for simulation purpose use finite difference method in place of the finite difference method. Actually, as I told you that initially the finite difference method were used for solving PDs, but now people move on the finite element method. So, for simplicity, consider the elliptic PD. Consider the elliptic PD. Obviously, in 2D, we start with 2D finite difference, and I will tell you what is the problem in finite difference method, and then finite element method come in picture. So consider this del u is equal to f of xy, and xy belong to the domain, which is obviously the subset of R2, and u is equal to 0 on the boundary of this domain. So I am saying, suppose for this problem is say 1. So in finite difference method, what happens? So this del operator, obviously you know that this is the del upon del square upon del x square, del square upon del y square. So second order partial derivative occurred in this equation. Okay, by using finite difference method, people approximate the derivative at functional values. Okay, so for example, suppose we have a u dash at x, so we can discretize. First of all, we suppose this is 1D problem, and domain is 0 to 1. Discretize the domain into suppose we have the n points x1, x2, and xn. So we will discretize this is one ith point. So discretize the derivative at ith point, because I am using the forward difference method. So this is this, and divided by, there is some step length. Obviously I am saying h is the step length, which is xi plus 1 minus xi, because the finite difference method generally worked on uniform mesh. Uniform mesh means if the step length between each node is the same, which is I am saying h is xi plus 1 minus xi. So this is uniform mesh. You can say this is uniform mesh. And so divided by this and plus order of this. This is the truncation error, you can say. How to find this? This is the order of the truncation error. Just apply here Taylor series and subtract and divide by h, and so finally you will see that this order is this one. This is for first order. Similarly, second order, I am not going in detail of the finite difference method, because my main motive is to teach the finite element method for elliptic as well as parabolic PDEs. Okay, so now I am just giving the motivation, because why the finite element method start. Because initially the finite difference method were used by people for solving the PDE. So now here I have considered this one. So now I will explain when I will solve this PDE by using finite difference method. So what type of problem I face. So to reduce, to overcome that type of problems, people start using finite element method. Okay, so now come to the for solving this by finite difference method. I like to told you that our domain I am considering for simplicity. Consider this domain is just a square domain. It is open and this is closed, no problem. But at the boundary, the solution is given. That's fine. So this is our domain here. This is our domain. This is 0, 0. You can say. So in one direction, this is x-axis direction, and this is the y-axis direction. So first of all, discretize the domain. So I am discretizing the domain, and then after that, approximate the derivative at the mesh points. So because this is our two-dimensional problem. So here I am saying this is suppose x0 I have denoted by this x0, this is x1, this is x2, and suppose this is at 1, this is suppose xn. Okay, and in the same direction, suppose this is y0 here, and this is y1, and this is yn. And suppose this some point is, this point is xi and yj, where I is equal to j equal to I equal to 0 to n, and j is equal to 0 to n. But let's assume again here result that n is equal to m. And I am saying that this is the step length. So I am assuming h is the step length in x direction. And same here, because I am saying that n is equal to m. So in h direction also I am assuming that h is the step length. Means I am taking the both step length in x direction and the y direction, it is h, that is same. But you can take this is h or this is k. People use this also. But for simplicity, I am just explaining that you can take h step length in x direction and h is the in y direction. Okay, so this first of all discretize the domain. This was our domain, and discretize in mesh point. So the mesh is what now? The mesh of this is xi, yj, I is equal to 0 to n, j is also 0 to n. So this is our mesh now. Okay, so this is the null point xi, yj. So at this point, now approximate, because this our elliptic PDE, this contains the second order derivative, partial derivative in x direction with respect to y. So by using finite difference method, finite difference method, approximate the partial derivatives at the point xi, yj, at this central point. Okay, because you can see that this is x direction. So here this partial derivative, if I will approximate, so the j direction will be fixed here. So what I am saying, this is central point. So in this one, this I will move from here to here, and because j at this point yj is fixed, so I will move in I direction. Yeah, you can say x direction. So this is x0, x1, x2, and so on. So this our partial derivatives, because this is a partial derivative of u at this point xi, yj. Here I can say one thing, this j is fixed. This is approximated by, yeah, you can say this is written by xi plus 1 yj minus 2 u of xi yj and plus u of xi plus 1 and yj and divided by h square and plus order of h square. Truncation error of in second order will be this. Right. Okay, so now here you can see that the j, yj, this is fixed here. Okay, so now and but this is equal. When you will remove this truncation error, so this will be approximated. Then in that case we will write like this. But here this is equal to now. Okay, so similarly the second derivative, this derivative at the point xi, yj, but here you can say that this is I is fixed here. I fixed here. Because here j and j, so j was fixed, but now here this is I is fixed here. So this is equal to u of xi yj plus 1 minus 2 u of xi yj and plus u of xi yj minus 1 and divided by h square, because I have considered uniform mesh, and plus order of h square. This, for simplicity, I can write this as just u I plus 1 j minus 2 ui j plus u I plus 1 j and divided by h square and plus order of h square. And similarly, you can write in this form just for simplicity here, the u of xi yj is equal to uij. This is just for simplicity. Okay, so now this become ui j plus 1 minus 2 ui j and plus ui j minus 1 divided by h square plus order of h square. So now say this is 2 or say this is 3. Now put 2 and 3 in 1. Now put 2 and 3 in 1. So finally what you got, and because this h square is common, take common, and this is minus 2 uij, this is also minus 2 uij, so this will add, so this become 4 uij, and I am taking the common. Okay, put 2 and 3 in 1, and what we get? We get is this 1 by h square is common, and ui minus 1 j, ui plus 1 j, and minus 4 ui j, and plus this was for I minus 1, I plus 1. So now the same thing, ui j minus 1, ui j plus 1, and equal to, because what I did, first I discretized this PD at the point xi yj. So this xi yj is equal to f of xi yj. So right hand side is also xi yj. I think this is fine. Okay, and obviously that there is also one term plus order of h square. You can see that this is order of h square in both of the approximation. Okay, so now, but this you cannot solve this equation directly because order of h square is also here. So what I will do now, I will leave this term. So I assume that this is the exact solution. U is the exact solution at the point xi and yj. Okay, so now if I will leave this one, so this solution is not exact. Now it will become approximate solution. Okay, without explaining this is what you can say, there are 5 points. So this is 1 point xi yj, xi minus 1 j, xi plus 1 j, xi j minus 1 and j plus 1. So this, sometimes this is called 5-point formula. This is called 5-point formula. Or this work, how this work? This will work like this. Suppose this point is I j, this is I minus 1 j, or this is I plus 1 j, and this is I j plus 1, and this point is I j minus 1. So this is called 5-point formula for solving the elliptic PD of second order by using finite difference matrix. So now, as I told you that we cannot solve this equation, say its name is 4, so I'm saying this equation is 4. 4 cannot solve directly. 4 can't solve directly because of this truncation error. So now what I will do, I will leave this term and assume that I will define one more thing. Define here U, capital U. This is capital U ij, or you can say capital U at the point xi and yj. I and j are the same, running from 1 to n. J is also 1 to n. Define this is the approximate solution. Is approximate solution of the PD1. Okay, so now if I leave this term from the equation number 4, then 4 become in term of the approximate solution, and these solutions are denoted by capital UI and J. So define this and omit, you can say omit order of H square from 4. We have what we have. So we have and I am taking this minus H square that side. Okay, so this become capital UI minus 1 J plus UI plus 1 J 4 UI J plus UI J minus 1 UI J plus 1 and equal to minus H square F of this. I am saying this as Fij means F of Xi and Yj. This is fine. So now this where and apply the boundary condition. What is boundary condition? Boundary conditions are given u is equal to 0 over the boundary. Just I am again making the domain. U is equal to 0 over the boundary. So at here, here and here and here, the solution is already given, that is equal to 0. So I can say with what are the boundary conditions here? You can say this one, U0M, so U0J is equal to U and J is equal to 0 for all J, and UI0 is equal to UIN is equal to 0 for all I. This one. Okay, because these are the boundary conditions. Understand? Or you can write this is equal to 0. This means what? U of 0y is equal to 0, U of 1y is equal to 0, and U of x0 is equal to 0, U of x1 is equal to 0. These are 4 boundary conditions because this is 2-dimensional problem. Understand? So you can see that from this equation, 0 is fixed here, this is 0, and J is running because Y is running here. So you can say this is equal to 0. Second one, this is what I have written here, n. This means at this n, at x is equal to xn, so this is value 1. Last point is x, this is last point xn, so that is equal to 1. So this is second one. Similarly at here and here, here and here, again this also J0. So you can assume. So now whenever you apply the boundary condition, so this means this U0, 0, U01, U02, U0 and UN all are given to you. Similarly here. So this means just we have to compute the solution inside this domain, not at the boundary. Okay. So now this equation, say this 5 equation can be written in form of a matrix. This 5 can be written as a matrix form, this, where you can see that capital U is a vector which is the solution, and that is equal to U11, U21 and UN minus 1, 1 and U again, because 2 will run again because this is the last point of this one. Suppose I am saying this is my discretized domain. add this, and then second and third. So this. Last will be n minus 1 and minus 1. Okay, this is the solution. You can see that this contain all the solution. This, and this, and similarly in this direction also. So all solutions are denoted by this. U11 means at U of x1, y1 means the this solution, finite difference method gives a solution at the nodes only. This is also one drawback of this method. I will explain later. So now U is equal to this, and where A is what? A is equal to, this is the diagonal matrix, right? Where diagonal contains B1, B you can say B and B. And B is what? B is a matrix whose tridiagonal matrix which contain the element 1, 4. Tridiagonal means this will be like that. You can say B is equal to what? 1, 4, 1, 0, 0, 0, 0. Or 0, 1, 4, 1, 0, 0, 0, and so on. 1, 4, 1. So this type of tridiagonal matrix will come here when you will make matrix of this. You can see from here also. This 4 is there, okay, and rather this. So this will be minus 4 because this is here minus 4 and minus 4. So this is diagonal and this is minus 4. Okay, so means that A is what? Whose diagonal element are nothing but B matrix. B is what? Diagonal matrix containing this type of elements. Okay, so now you can see that the structure of a matrix. What will be the structure of matrix A? This is the matrix whose element just contain 1, minus 4, 1, and all other elements are 0. So this size of B will be what? Size of B matrix will be n minus 1 cross n minus 1 due to because we have applied the boundary conditions. So we are excluding boundary solutions. So that's why it is n minus 1 cross n minus 1. So if you will see that, what is the dimension of A? A will be n minus 1 cross square and square. This. Okay. So A is a sparse matrix. Sparse matrix. Sparse means the matrix whose maximum entries are 0. That is called sparse matrix. So here also, because you can see that B matrix has just first 3 elements of the first row are non-zero, all other elements are 0. Similarly, in second row, just 3 elements are non-zero, all other elements are 0 here. So this becomes sparse matrix, and A is, you can say, A is symmetric, because if you will transpose of B matrix, so it will be again the same thing. Okay, symmetric matrix, and this is diagonally dominant. Diagonally dominant. Diagonal dominant means what? Diagonal dominant means you can say that a matrix is called diagonal dominant if its diagonal element greater than equal to 0, j is equal to 1 to n, and j not equal to I, like this. If this happens, so we can say that that matrix is diagonally dominant. So this is diagonally dominant because the sum of this element, the diagonal element, suppose I'm okay, so you can say this one, it's 4 minus 4. This is okay, but I think last and first think I should start like this. -4 and 1. Okay, -4, 1. This is okay. So this is diagonal dominant. There is no problem. Okay, so now, so question is that this is what? This is suppose I'm saying this is 6. This is solvable or not? This is the question here. Is this solvable or not? Because just a minute, I think so this will be -4, yeah, it will be like this, and you transform and this also. Now I think this is fine, because the structure of this will be like this, and okay, yeah. So question is that is this solvable or not? If this is solvable, then we can find its solution, and that's fine. But our A matrix is symmetric and diagonal dominant, then A, B inverted. And one more property A has also here. One more property, A is irreducible. A is irreducible, symmetric, and diagonally dominant. So inverse of A will exist. It is invertible. Then this exists. Because U is what? U is the solution of this equation. This is system of linear equation. So if A is invertible, then this is fine, and we can find its solution. So this is okay. So now, in stability point of view, about the 6, because A is what? 6 is the system of linear equation. So what about its stability? If we will go detail in the finite difference method, so this is stable with the L infinity norm. So for stability purpose, stability point of view, if you will see, 6 is stable system. Stable with respect to L infinity norm. If this can be written as norm of U, L infinity norm is less than equal to this, where C is C is also here, where C is independent of H. H is what? H is the step length, and you can say this is what? Maximum of, this is maximum of Uij I j less than equal to. So this is the maximum norm, or you can say L infinity norm, and this is the stable with point of this. You can see why, if this is bounded by this. C is constant here, independent of H, and F is what? F is known thing here. Obviously that this will be some finite thing. So we can say that here the solution U is bounded by F. So totally depend upon capital F, or capital F is what? Capital F here is what? This is minus H of its element are like this, Fij, H square, and F of Ij. So means the stability of this solution, capital U depend upon capital F. Capital F is nothing, the element of H square and Fij, means the source term. The source term of the PD is small f. If it is okay, then we can say that our solutions are stable. Okay, so now one more thing is here. If this was just infinity norm, we can also discuss its stability with another norm, for example Euclidean norm. It is also possible. It is also possible to discuss its stability, with respect to Euclidean norm. Okay, so I'm saying that u minus u, let u is the here is the exact solution and u is the approximate solution, which I have defined already. Capital U is equal to this, and okay, I'm defining here the u bar. U bar is what? The same thing, u11, but this is a small u, which is the exact solution. u21, u n1, and last u n minus 1, n minus 1. Let this is the error, which satisfy this, you can say the solution here, because u bar is also solution and capital U is the approximate solution. So obviously this is the error here, or so error can be bounded by. So now start with A of u bar minus u, that is equal to, if now I'm starting with this, A u bar minus A of u, take just A inside, so this become A u bar minus capital F from the equation 6, because capital A and capital U, this is nothing, capital F, capital I have denoted by this. So say total this, if suppose I am saying this is ta, where ta is what? Ta is a vector, because obviously this is a vector, capital F is also vector. So difference between two vector, again a vector. So tau is a vector representing the truncation error, representing the truncation error, and hence the stability is bounded by like this, u bar minus capital U infinity, that is bounded by C, this ta, and that's the equal to C, because this is what? This is the truncation error, and as I told you that the truncation error is the order of h square. So this is C h square. So here C is what? Here where C depends on maximum norm of fourth order derivative. Fourth order derivative of exact solution, that is small u. So this is this C, when actually I am just giving here brief, not the whole derivation. I told you that it is also possible in Euclidean norm. So this is another concern. So this is just, I have written that we can do its stability estimate in the Euclidean norm also. Now in the continuous way, I have tried to find its, this is error. You can say error in the L infinite norm is bounded by CH square, where C is depend upon the fourth order derivative of the exact solution U. If you can see that this is constant, and second thing important is here the fourth order derivative, means that the exact solution has fourth order derivative exists, then we can estimate this, otherwise no. So that's why what I am saying here. So sometime what happens that it is not possible that solution of the our elliptic equation, yeah, you can say our problem is not the differentiable up to fourth order. So in that case, this to find this estimate is difficult one. Second thing, if we choose the okay, I'm writing these points because these are important one, which motivate us to go to finite element method in place of finite difference method. So first point is that impossible to achieve u belong to C4 over the boundary, because here this C depend upon the fourth order derivative. When you will go in detail of the derivation of this stability estimate, so you will see that this C depend upon the mode of the fourth order derivative. Okay, so but it is not possible always for every problem. So that's why this is a difficult task. If this is square, because I have considered our domain is square, then you can go maximum u belong to C2 intersection C of this one. Here for the our original problem minus del u is equal to f. If our domain this is square only, then our solution will belong to u belong to C2 and this. So what the finite difference people do, they assume that the fourth order derivative of the solution exists. Okay, so if they assume that's why that is okay, but 4 is square, so maximum this go up to u belong to C2 intersection of C, means at boundary. Oh, so this is also this is boundary here. So this is boundary because bar is here, so boundary including here. So at boundary it is maximum continuous. Second point is that if we choose very nice boundary, then you may be C4. Means here that if this our boundary of the domain is very nice, very nice, you can see C infinity, you can say it is always so in that case we can say that this is okay and this will exist. So why these methods are popular? Because these are easy to apply and easy to find solution and gives good approximation. So that's why the finite difference method are popular. But what are the disadvantages? What are the disadvantages of the finite difference method methods? So first one is difficult to apply over irregular domain. Irregular, or you can say difficult domain. Irregular domains means what? Suppose our domain is like this. Okay. So what you will do? You will do again the same thing. You can see you will discretize the domain, as I told you that, and again you will discretize the domain. So you can see that this solution, this or this type of boundary you cannot compute at here and here. So this is difficult to apply. So at this place, because these are not rectangle here, so this is okay, this is okay, and this is okay. So if this type of domain we have, so we cannot apply the finite difference method, in that case at the boundary there will be too much error, so total error, order of error will become down. So that's why, so this is difficult to apply this type of domain. Second one, as I told you that it requires high regularity for the solution. As I told you here, if U is C4, then we can compute, we can estimate its stability and other things. So it requires smoothness of solution, or you can say high regularity. High regularity of the solution. Second thing, you can see that if you have to find the solution, nice solution, yeah, you can say more accurate solution. In that case, you have to refine the mass. Refine means you have to increase the number of points. When you will refine, as I told you that the domain of this is like this, and this is a discretization here. When you will refine the mass, the system of this system, as AU is equal to F, this system becomes very big. Okay, means the dimension of this A will be high and high. So in that case, it is difficult to solve this system. Means it is difficult to refine locally. Therefore, because we cannot, for example, in finite element method, suppose you want to just refine the mass in this domain, so we can refine the mass locally. But in finite difference method, it is not possible to refine the mass locally. So this is one more disadvantage is, you can say that we cannot refine mass locally. So, and one more point is that the obtained solutions be at the, because what we will do, we will find a solution in finite difference method at only the nodes. At the nodes. If you have to find solution at any point except the nodes, so I am saying that to find solution at this point, so you have to go some more interpolation. So the obtained solution be at the nodes or grid points. At the grid points, therefore, to compute the solution at another point except the nodes, you have to use some more interpolation, so which will decrease the error, because if you will do one more approximation, so there will be some loss of error. So these are some 4 points where finite difference method are difficult to apply, but people are using in spite of these points, because these methods are easy to apply, and gives a good approximation. Actually, for second thing, if you have to go analysis point of view, so you have to assume more smoother solution or more regular solution. So, however, finite element method overcome all these points. Means finite element method easy to apply irregular domain, And here, just to solve this type of equation, we need less regularity. And and in finite element method, we can refine the mass locally also. And the last point, in finite element method, we assume solution in the some in we direct find solution if you want to find the solution except at the node also, because in finite element method we assume solution uxy is equal to summation of some constant, unknown constant, and the some basis. So basis we have known. Suppose we have the solution is like this, ux is equal to some ci and phi I of x. So if this solution is known, so just put, because these bases are we have, these CIs we have, so and U will be this in the linear combination of these things. So you can put any point here, so you can find solution. So no need to use another interpolation to find the solution. So now these are the points which motivates the people to work in finite element method. So now we will come to the finite element method. So but finite element method, we need some requirement of, as in the starting of the lecture, I told you that for finite element method we require some basic concept of functional analysis, and then some inequalities, and then we can move to the finite element method. So now some basics of finite element method. People say FEM also, FEM, FEM, finite element method. So let this domain, I am assuming that omega is a domain, be a bounded domain in RD. D I am taking here just 1, 2 and 3 with smooth boundary that is denoted by this one. So first of all define L2 space. What is L2 space? I think if you are done master in mathematics, so you know already that what is L2 space, LP space, so Hilbert space and Banach space. So I am assuming here so this contain the function which are square integrable function. Means that all the functions, this contain all the functions whose square integration is finite. Or you can say that these are square integrable functions, because square of these functions exist and that is equal to finite. Exist means the integration should be bounded. So this is bounded. And the mapping defined like this. I think you know already this is the inner product. This is inner product from L2 cross L2, because this is L2 space here, and 2R is defined as, you can say, inner product of U and V, that is equal to and Vx. So under this, so this become inner product space and then become later Hilbert space. Okay, so this satisfy all the property. Okay, before this I am just telling you what is the norm here. If you remember what is norm, norm is a function from some vector space, or you can say that some vector space, yes, go to R, or sometimes you can say C also. C is complex number and R is the set of real number. So this is function. If this satisfies some property, so we can say this is a norm and this always greater than equal to 0. Second one, if this is equal to 0, if and only if u is equal to 0. Third thing, norm of alpha u, that is equal to mod of this and u. And fourth property is satisfy u plus v less than equal to norm of u plus norm of v. So because we will play with norm always in the analysis of finite element method, so it is necessary to what is the definition of norm. Second definition, inner product. So inner product, again the same thing. So this is the inner product from V cross V to R. So first one is that if it is R or C, you can say. If it is C, so then we can take, otherwise this is fine. The first one, UV, inner product of this is equal to VU. If it is not the complex number, then this is fine. Okay, so second is that second property is that this is the linear property. Alpha U plus beta V W is equal to alpha UW plus beta VW. And the third property is here again positivity. This is U V is greater than equal to 0, and the UV is equal to 0 if and only if U is equal to 0 and U is equal to 0. This. So, but here this inner product not necessary that this satisfies. Here in L2 space, I am saying that this is you can say some kind of force property also, means U is equal to 0, not necessary U is equal to 0. Okay, so this concept we are leaving here, so that's why. So we can say in L2 space, the fourth property of inner product not necessary satisfied. Means that if the integral is 0, so not necessary that the element is also 0. So I can say that means this one, say this is star here, I can say star, okay, this is star satisfies all the properties of inner product, all the property of inner product except this one. V of V is equal to 0 implies V is equal to 0. So means this doesn't satisfy. So here, so we will use the concept of almost everywhere here. So V is equal to 0, not necessary that V is 0. Means this may happens, the V of inner product of two elements is 0, but not necessary V is equal to 0. Okay, so I can give an example of V is identical to 0 here. So for example, I can assume that our domain is equal to 0 to 1 and define for n is greater than 1, define a sequence Vn that is equal to n and 0 if x is equal to 1 by n. Okay, this is if x is equal to 1 by n and elsewhere. So you can see that 0 to 1 Vn square dx is equal to 0. Okay, this but here Vn is no. Means this is what? This is Vn, inner product of Vn, and that is equal to, by using this definition, so this becomes Vn square, and that is equal to 0 because at a point the integral becomes 0. So this is 0, but Vn not equal to 0. So that's why we will here. So here we call, here what we call this? We call V of V is equal to 0 implies V is equal to 0 almost everywhere. I think you know, have you listened this term in functional analysis? Almost everywhere. Means the almost everywhere means what? Where this doesn't happen, so there the norm of the measure of that set will be 0. Means where this is not equal to 0, the norm of that measure of that set will be 0. Okay, so here I have defined just L2 function. This L2 space, this is L2 space, inner product and this. So this become norm space L2 with norm. If I am defining norm over here, norm of V, that is equal to VV 1 by 2 power 1 by 2, or you can say norm square, that is equal to VV equal to integration over this norm of this total power dx, total power 1 by 2. So this is the norm. So with this norm, L2 become Hilbert space, because first this will become okay, this become with this norm, L2 with norm is inner product space, then it is complete inner product space. Okay, this become complete inner product space means, what do you mean by complete? Complete means every Cauchy sequence should converge. Every Cauchy sequence is convergent, because with this norm and with this inner product, first this become inner product space, and if it is complete, then this is called Hilbert space. Then it is Hilbert space. So means that if an inner product space is complete, then this become Hilbert space. Similarly, also in the norm space, if norm space is complete, then become Bragg space. Okay. So with this norm, if you will define this, you can prove that easily. This become complete, and then this become the Hilbert space. Okay. So there are many examples of also Hilbert space. Rn is the Hilbert space. Cn is also the Hilbert space. So these are some examples of Hilbert spaces. So now this was L2 space. Actually, L2 space is too much use in the, I can use here the word too much, because this too much use in the finite element method, because most of the property of Hilbert space, L2 space, we use in the finite element method. So now, so some more property here also of L2 space. Some properties. Number one, this space C omega. This is set of all continuous functions. Means all the functions contain this one. You can write, if you want to write, f such that f is continuous here. may not be subspace of L2 space. Means that every continuous function is not necessarily the L2 function. How this? I can give an example for this here. Again, the domain consider here 0 to 1 open interval, and Vx I am saying 1 by x. You can see that over this domain 0 to 1, Vx is continuous. This is continuous on the interval 0 to 1 because this 0 is not included in this domain. So this is continuous, but here V doesn't belong to L2 space. Since because when you will find the square of this integration of this square, you can say V square dx, that is equal to 0 to 1 x square dx, and that is not bounded. When you will integrate this, so you will see that this go to infinity. So this is not bounded. So this means V doesn't belong to L2 space. Means that every continuous function not necessarily the L2 function. Similarly, reverse also means maybe that V is belong to L2 but not necessarily in continuous space. For example, suppose I am defining Vx is equal to 0 and 1 by 2 and 1 by 2. So here is less than and here is 1. This is a function. This V is discontinuous function. At x is equal to 1 by 2. So this is discontinuous, but this is the V belong to L2 space. Here again this domain is this. Okay. Domain is this. There is no problem. Because this is discontinuous at the point 1 by 2, but here you can see that but V belong to L2. Again you will find its square of this, so you can see that is finite. So it is continuous but not in L2. So means that this is the reverse one. Means this isn't doesn't mean that a function is continuous. It is in L2. It is in L2. It is in C function, C omega form. So this is not necessary. Second property that let L1 space function. L1 means just integrable function. These L2 means square integrable function. So L1 is defined by like this V such that integral over this is finite. This is L1 function. Okay, means that these are the L1 functions. The space is this space, and L2 is continuously embedded in L1 space. This means what? All the function of L2 space are in L1 continuous. Obviously, understand? So I am explaining this. What is embedding means? Embedding means between two spaces. Two spaces are embedded if there is some embedding between these two. And I am here writing continuously is different thing. Means continuously means that embedding is continuous. And so first I think I should tell you what is embedding. Continuous embedding. Continuous embedding means two space, I am saying X space and its notation is like this: is continuously embedded in Y. These are some norm spaces. Two norm spaces. Continuously means both are X is continuously embedded in Y. This means what? Every element of X is in Y. That is, you can say X is like this. Second, when there is a mapping, suppose I am saying I from X to I such that I of X is equal to X is continuous. Okay, this is continuous mapping. This is continuous mapping and continuous mapping and means that every element of X is equal to X in Y, and the norm of X over the Y is bounded by C of X like this. Or you can, if you want to just because this is X here, so you can say U or U for all U. It will be like this. So this norm of the element over the norm over Y is always less than equal to norm of U over X. So this is the means L2 is continuously embedded in L1 space. You can say that this L2 is in L1. Okay, so but the reverse, but this is for this hold for bounded domain. This hold for for bounded domain. This is important. This would be bounded domain. If it is not bounded, then it is not necessary here. So, for example, I can say that, for example, for unbounded domain, it is not necessary. Our domain is our domain is 1 to infinity. This is unbounded domain, and consider Vx is equal to 1 by x. This V belong to L1 or not? This doesn't belong to L1, but V belong to L2. Understand? This means what? L2 contains in L1. L2 contains in L1 when if it is bounded domain. Otherwise, see, you can see this function belong to L2. This belong to L2, but not in L1. That's fine. So one more space is also here. That is the locally space of all locally integrable functions in some domain omega. So means that this is what this is denoted as LOC here. This is locally. This denote LOC locally, and once means just this one means just integrable function. Means that this will contain those functions V belong to L1 over some K. This doesn't mean that all the functions of this are integrable over the full domain, but they are locally integrable. Means that V belong to L1K. K is some subspace of omega for some compact set K with K bar contain. So this is the locally space, locally integrable space. Means V belong to V is integrable, but locally means there exists some compact set K whose closure is contained in this omega and this omega and this is fine. But it is not necessary that the F belong to if V belong to this L1 locally, not necessary V belong to L1, not necessary. Okay, so now this was some L2 function, L2 space, L1 space, L1 locally, because I will use these spaces in finite element methods. So that's why it is necessary to define these spaces and their properties. So similarly, there are also LP spaces. Similarly, we can define for this LP spaces for 1 to infinity here. So the space of all pth integrable function, pth integrable functions, it is denoted by like this LP space, and it is denoted by this, and their norms are defined as, their norm is defined as P here, or sometime you can say LP here, or if you write P here, that is also no problem. This is P, that is equal to integral over the domain this is P. This is for what? For P to less than infinity, and this norm is defined as at infinity. This is denoted as, or you can write this as you can define like this, L infinity over this, that is equal to essential norm supremum here. Okay, this is just sup of V of x, and x belong to essential norm. This is, you already know what is the essential norm here, or if you want to define what is this essential norm, you can define, means like this, f of this infinity, that is equal to infimum of all c greater than or equal to 0, such that mode of this is less than or equal to c for mu almost for mu almost every x belong to this. Means that just you have to take infimum of all c's which are bounded. Means if this f is bounded by c's, so you have to take the infimum of all these c's, that is the essential norm. Okay, so these are some LP spaces. So now come to the distribution theory. Distribution theory is what? Distribution theory is the generalization of the derivative in large space. Means that suppose in on the real space we define derivative. So in the similar manner, distribution theory help us to define the derivative in the large spaces. So like Hilbert spaces and this is. So distribution theory. So this is what we generalize the concept of differentiation to the functions belonging to a really large space. So this is the distribution theory. What this do? This connect the derivative concept of functions in the large spaces. So first, this there is a multi-index. What is multi-index? Multi-index concept is also there. So I am saying alpha is the multi-index. So I am saying alpha 1, alpha 2, alpha is a n-tupled with non-negative integer, with you can say with non-negative integers elements. Means that these alpha is elements. Means I am defining a multi-index here. Just alpha is equal to alpha 1, alpha 2, alpha n, and this is n tuples. Each tuple x alpha 1, alpha 2, alpha n. Each tuple is what? Is the non-negative integer here. Okay, so then define by if you have to define the order of a derivative in distribution theory. Suppose I am saying the alpha order. So alpha order means what? This is alpha order, but what is the value of the alpha? Alpha order value will be mode of alpha is equal to mode of sum of alpha 1 plus alpha 2 plus alpha n in mode sense. So you can say by order, I am saying that by order, by n order of alpha, we means mode of alpha is equal to summation I is equal to 1 to n mode of alpha. You can do, but it already non-negative, so no need to take the summation, the modulus also. But alpha here what? Alpha is equal to summation of this. Okay, so for example, I have to define the alphath order of some function. Alphath order of some function. So how to define this? Suppose I am saying the define alphath order partial derivative of a function. Suppose I am saying of function u. So I will write like this: d alpha u is equal to, that is equal to alpha u upon. So okay, this is mode, because mode means the what is the total value of this. This is, and suppose I am saying using x1, x2, xn. So here suppose this is alpha 1, x2, alpha 2, and xn alpha n. So this is the alpha partial derivative of u in multi-index sense. You can say that d alpha u total is this. Okay, mode of alpha is the total derivative here of u, and this partial derivative with respect to x1 is alpha 1 time and alpha 2 time for x with respect to x2, and similarly for xn time. So here obviously that alpha is what? Alpha 1, alpha 2, alpha n. For example, I am saying that suppose you want to understand about, I'm saying n is equal to 3, means 3-dimensional partial derivative, and then alpha will be, suppose I am saying to be, because alpha will be 3, so I am saying 1, 2 and 3. Okay, I am defining the fourth order derivative, suppose. So here mode of this is equal to what? 1 plus 2 plus 3. Oh, okay, this is 1 is equal to 4. So you can say d alpha u is equal to, or you can say, because alpha I have defined the fourth order derivative, so that is equal to fourth order derivative of u. So here this means with respect to x1 just one sign, with respect to x2 2 times, with respect to x3, with respect to x3 just one time. Okay, this is not the means if you want to just find the fourth order derivative, not only this 3, you can write one more thing, because total derivative is 4 here. So 4 you can write 0, 4, sorry 0, 2 and 2 also. Means that you can define here d4 of u is equal to the fourth order derivative of u, but with respect to x1 there is no derivative, so this is x2 is twice time, and with respect to x3 is also twice time. So this is the concept of multi-index. Okay, so now similarly, if in case suppose I am taking the mode alpha is equal to 2, so in this 3 and n is equal to 3 means 3-dimensional. So what will be total possibility when total sum is equal to 2? So its possibility will be 6 possibility. 6 possible derivative will be there. How? So you can say 2, 0, 0 and 1, 1, 0. This is second possibility. 0, 2, 0 and 0, 1 and 1. 0, 1 and 1, and one more is 0, 0 and 2, and one more is 1, 0, 1. So 2, 4 and 6. These are 6 possibility of the, because alpha is here 2, so total sum should be 2, 2, 2, 2, 2 and 2. So this is the multi-index. So one more term generally used, CM. CM over omega, that is equal to those functions such that their alpha derivative is also belong to C omega, and this mode of this less than equal to n. This is important. This means continuous and differentiable functions m time. Here those functions whose alpha derivative is also C omega, means continuous, and mode of alpha is less than equal to n. For example, I am just saying alpha is m is equal to 1 here. This means what? This means if I am saying, for example, I am saying m is equal to m is equal to 1 here. So what will be Cm v, those functions such that d alpha v, d alpha v belong to C, and mode of alpha is less than equal to 1, because m is what? M is 1 here. Okay, so this means alpha can be 0, means that v belong to continuous, and alpha can be 1, so 1 means its derivative, first derivative is also continuous. So only this will contain two type of functions. Those are the functions whose the function is continuous, their derivative is also continuous. But later I will explain that this is not the classical derivative. This is the weak derivative. Later I will explain what is the weak derivative and how this behaves. Means that if a function doesn't have a classical derivative but it has a weak derivative. So I will explain later. So now, so this was Cm, but here there was no bar here. So means that this contains a function, continuous and differentiable function up to mth order. Okay. So now one more term similar to this, Cm omega bar. Okay. So this is what is. This is set of continuous and differentiable function up to m is has, you can say has m time continuous differentiable functions with uniform continuity up to order m. So this is the just bar I have used here, but uniform continuity maintained. These functions maintain the uniform continuity due to bar of this one. So now, there is also a space C infinity. C infinity, this means a space of infinite time continuous and differentiable function. Okay, continuous and differentiable function. So here you can write C infinity. Just this is intersection of Cm of this. This you can prove easily that intersection of all these functions is. So now one more thing is support of here. Support of a function. What is the support of a function? Support of a function is denoted by SUPP. Support of any function, suppose I am saying support of this function means is the set from omega where this function is not equal to 0 and bar of this. Means support of V means this set contains where this function is not equal to 0. Means this is the set of functions, set of element of this omega where this function V is not equal to 0 and closure of that. You can say closure of that one. This is the support of this. If this support become compact, so we can say compact support. Compact supports means if there exists a set K which is compact, okay, in this continuous, if this set is compact, and support of V contain this, then V has a compact support. compact sport. Okay, with respect to this omega, with respect to omega. So this become compact sport. So if we have one more set, if you define here just Cm, this is just C infinity, this is sport, and one is compact sport. Okay, so or you can define in another way. There exists a K compact set, compact subset of this such that sport of V contain in K contain in omega. So we can say that this sport is defined as is compact. Okay, so there is some simple example of this type of function. So over this, suppose our domain is like this from here to here, and these functions are defined like this. So here 0, here 0, but over this is non-zero. So this type of functions have the compact sport, or these are some special function. You can say it's a Lagrange interpolation if you have studied. So we will use this for the basis function of a finite element method. So one more thing here, if we can define C0 infinity, or sometimes people write here CC infinity, this one. You can understand easily now. C infinity, you know already that this is the function which are continuously differentiable in finite time. But this means just compact sport. What is this means? C. The functions would have the compact sport. So this means the space of all infinite differentiable functions with compact sport. Compact sport in, obviously this is important, compact sport in omega domain. So what I am saying, this is our domain A to B. So this function have compact sport over the domain this A to B. I can give an example of one more example of this also, if you want to see. So one more example of this. Domain is here. This is R. R is the domain, and phi of x function, I'm saying phi of x, this is equal to e to the power minus 1 by x square minus 1, 0, mod of this less than this. This function phi belong to C0 infinity. You can prove easily also. This function is continuously differentiable in finite time and have the compact spot or just minus 1 to 1. Otherwise it is the 0. So this is the C0 infinity function. So now come to one more definition, then we will move to what is the distribution and how to define the distribution derivative. So there is a structure on C0 infinity, this type of, means we can define over this space some functions which are also sequence of functions which are also converges. So then we can define one more space here with respect to with respect to which the convergence of a sequence suppose I am saying phi n is a sequence converges to this function phi n, has the meaning that is, you can say that I can say that is phi n converges to phi. This means phi in C0 infinity, this space, if satisfies the properties, satisfy number one, there is a common compact set. There is a common compact set. I am saying that set is K, and that is common in omega with K bar contained in this omega, such that support of phi n and support of phi contained in K. Means that's why I am saying that a common compact set K means phi n and phi. Means I can say that this sequence converges to this function in this space if first condition is that the support of phi n and support of phi have the common support. Okay, both support contain in K. There exists a common set K which satisfy this one. And second property, you can say second one, d alpha phi n converges to d alpha phi uniformly in K for all multi-index alpha when C0 infinity this is equipped with such a topology, we call it D of this, the space of test function. Means we have defined another space here, d omega. What is this space? This space contains all the element of C0 infinity, but they have this one, phi n converges to phi. This type of functions this have, and second one, so they form some topology, and that topology is denoted by d omega, and we will say that, or you can say that that is, you can say this is equal to what? Those functions belong to C0 infinity such that there exists K subset of omega, and compact, this is compact set, and support of F contained in K. So means d omega are this type of set, this contains this type of function, belong to this, and this belong to compact set. So and every function have the this property, convergence property. This is converges to this in this one. So we can say support of phi n and support of phi is belong to is subset of K here. So this was a definition of another space. Now come to the definition of the distribution. Definition of distribution. What is distribution here? T is some mapping from d omega to r. This is d omega already defined. It's called distribution. It's called distribution if T is linear and T of phi n converges to T of phi as phi n converges to phi. So phi in d omega. So then this T is called distribution. First is that this is linear. Obviously we can prove easily it is linear. Linear means T of alpha u plus beta v is equal to alpha T of u plus beta T of v. Second thing, this if this converges to this as this converges to this. Answer means if this converges, so this should be converged. T of phi n converges to phi n. So we can say this is the distribution. So here the space of all distributions. What is this here? T is defined over this set. If I am containing, this is dash. Here you can see that this is just d omega. This is d dash omega. What is this d dash omega? D dash omega is, you can say, space of all distribution defined over this. We can say this is all T such that T is distribution on the means set of all distribution, or you can say which is the dual, if you remember, dual of this one. This is the dual of this space. Okay, so now so one more thing I want to just give to here, the example of the distribution. Every integrable function defines a distribution. Defines a distribution. Means this is the this is example. Every integrable function is an distribution. You can say it in this way. So I am saying let f belong to L1 space. This means I have to prove that every integrable function is distribution. So f belong to L1. So this means f is integrable function. And then for phi, I am taking phi belong to this space, which is already know what is d omega, and define a mapping like this, f phi and dx. Say this is 1. Okay, I have defined this. So I have to prove that this is a distribution. So for distribution, you have to prove that T is linear. So it is very easy to prove it is linear, since first T is linear. T is linear. Just start with f of phi 1 alpha plus beta phi 2, that is equal to over omega f alpha phi 1 plus beta phi 2 of dx, and it is easy to write this as alpha integral over omega f phi 1 plus and beta integral f phi 2, or that is nothing, alpha t f phi 1 plus beta t f and phi 2. So this is linear. This was very easy, just for your information. So now second thing you have to prove that. Second is that if this converges to 0, sorry, phi n converges to phi, then this t of phi n converges to t of phi. You have to prove this also. So given is what now? Given phi n converges to phi. Okay. So this means, or you can say that phi n minus phi is equal to 0. This is given. Required to prove Tf of phi n converges to Tf of phi. Okay. So now, from here you can start with this one, because you have to prove that the difference of these two goes to 0. So I am starting with this one, minus Tf of phi. So you have to prove this, this goes to 0. Okay, so now what is this? This is equal to, apply the definition of Tf. So this become integral f phi n minus integral f phi and mod of this over omega. So that is equal to, take common f and phi n minus phi and dx, and obviously that this goes to 0 as n goes to infinity. So obviously this goes to 0 as n goes to infinity. So this is just easy to prove that t phi n converges to Tf. So I think for today I am leaving here. I am stopping here because this time is over now. So tomorrow it is very important, because tomorrow we will start the some Sobolev spaces, and then how to tackle the elliptic problem by using the finite element method. First we will start with one dimensional problem, just simple u double dash is equal to fx, and first we will apply the finite element method over here. This is just one dimensional ordered differential equation with some u is equal to 0. Then go to the two dimensional problem like this, del u is equal to f and u is equal to 0, and then in third lecture we will continue this for the parabolic type problem like this, and u is equal to f type problem, and in the last lecture we will stop here. This is for just finite element method. For last one we will use the differential quadrature method. This is more theoretical point of view. This is differential quadrature method just for simulation point of view for the PDEs. Okay, so how to implement this method in the MATLAB also, I will try to cover this if time allow me. So now for today, thank you very much for attending this class. So if you have any questions, so you can ask, otherwise fine from my side. Yes.